So again, the way we name them is based off of, is it ionic or is it molecular? And in this case, the names are already given to you, so we can kind of figure it out a little easier. First one says lead, Roman numeral 2, chloride. So I'll just pronounce that lead 2 chloride. So, let's work on this together here. So, what does the lead Roman numeral 2 tell me? Has a charge of 2 plus. Okay, so what's the lead? Pb. So that's 2 plus. Okay. Chloride. What does that tell me? Ide. Nope. It's just ide just means just a non-metal by itself, just chlorine by itself. So grab your periodic table, which hopefully you have out. If not, pull it out real quick. Find chlorine. What's the charge on chloride? Yeah, it's 1 away, so it's just 1 negative, right. Okay, how do I make a 2 plus and a 1 negative balance out? So I'm going to need 2 of those chlorides, so I would write what? Pb what?
Just PB.
CO2. Right. Right, so I need 2, right? 2 of these negatives, right, to balance out that 2 positive. Right? Okay. I'll try 1 or 2 more with you, and then you guys can try some. Magnesium phosphite. What's magnesium symbol? Mg. What's the charge on magnesium? It's not given to me as a Roman numeral. Okay, it's 2 plus. Everybody find magnesium? It's in group 2, so it's 2 plus. Okay. What does ite tell me? It lost an oxygen, right. So first I'll figure, okay, so what's phosphate? One of the ones you had to memorize. You've now had 3 weeks to learn them. PO4, 3 negative. So phosphite must be what? 3. Lost 1 oxygen, 3 negative. Good. So how do I make a 2 plus balance out a 3 negative? What do I have to do? Yeah, so 2 and 3 will both go into what? What's these called multiple? 6. So how do I make there be 6 positives? Well, I need 3 magnesiums, right. And how do I make there be 6 negatives? I need 2 phosphites. So how do I write that? Parentheses, PO3, parentheses, 2. So now I have 2, 3 negatives, that's 6 negative. 3, 2 positives, that's 6 positive. Okay, let's do C. Nitrogen triiodide. How do I do this one? What do I write? What do I do? Ni3. How about the charges and stuff? It's the other one. Yes, what's the other one? These were both, oh crap. These were both ionic compounds, right? Yes. These are ionic, these are molecular. How do you know it's molecular? Because it gives us the tris and things like that, right? When you see that, you know it's molecular. So there are no charges to worry about. It's telling you nitrogen. Oh, triiodide, 3 iodines, right? Yes, that's all it's telling you. So those are easy. When they give you those prefixes, you know it's not ionic. There aren't charges to worry about. Okay, your turn. Try the next whatever. Is your D that D?
Yes.
Okay, I wasn't sure, because I changed a couple of these. I can't remember if I changed them before or after the handout was made. So. Okay, we'll try the next couple. Talk them over with your neighbor. Pause this. Okay, so let me go over a couple of these here with you. 10-4, so that means 10 is SN. The 4 means 4 plus. Oxide, okay. Keep going with the people. Ide generally means just the element by itself. Just the element by itself. So oxide just came from oxygen. So you find oxygen on your table, and it's 2 away from the noble gases, so it's 2 negative. So if you do the little crossover rule, you'll get this, which is not the final answer because 2 to 4 is not the simplest ratio. It's really going to be SnO2. Okay. Calcium nitride. Oh, again, ide. So calcium, you find it, it's in group 2, so it's 2 plus. Nitride, oh, non-metal by itself. It's 3 away, so it's 3 negative. So you put them together, you're going to have Ca3N2. So far, so good? Okay. Erase these. Dichlorine heptaoxide. Oh, I see these prefixes. Yeah.
I have a question about
Sure.
the prefixes in this one.
Okay.
It says heptaoxide,
Mhm.
which means 7,
Mm-hmm.
but doesn't the ide suffix mean there's only 1?
Mm-mm.
No? Alright.
It's like here it was Ca. Okay. First off, they're 2 different things: ionic and molecular compounds.
Okay.
It's a molecular compound. Second, all the ide means on the ionics even is that even here it was ide, but it was N2.
Okay.
Ide just means it's not combined with oxygens. It's not like nitrate. It's not like nitrite. It's just nitrogen. And whatever ratios of nitrogens you need is fine. Now, in this kind of compound is a molecular compound. So the first one keeps the same name. The second one always goes to ide. Ide doesn't mean anything about non-metal by itself because it's not an ionic compound in this case.
Alright, I get it.
Okay, so dichlorine means what? 2 chlorine, CO2. Heptaoxide? Oh, what? How many? 7, good. Okay. Sodium hydrogen carbonate. What's sodium? Na, it's in group 1, so it's 1 plus. What's hydrogen carbonate? It's one of the ones you had to learn. HCO3 negative. So how would those go together? Just put them together, right? NaHCO3. And I don't need parentheses, right? Why not? Because there's only one of them, right? If you have more than one polyatomic, then you have parentheses. Okay, barium, Ba. It's in group 2, so it's 2 plus. Phosphide, ide again. So that means it's not combined with oxygens. It's just a phosphorus right here. What's the charge going to be on it? 3 negative because it's in group 3. So Ba3P2. Okay. I hope you've been practicing those. So, okay. That's naming. But I will say again, that's probably the second biggest, most important thing we do because from here on out it'll be like, I don't know, I'd be like writing equations or trying to find molar masses or doing calculations, and it'll all be in names. Barium phosphide reacts with calcium nitrite. Write the reaction. If you don't know what phosphide or nitrite or anything is, then you can't do the next part, which is write the reaction. Then you can't balance the reaction, right? So I'm saying you really, really, really have to know the naming. So I will say again, go back to my little YouTube channel if you need to. If you need to, then watch the little videos on naming. They're super helpful, I think, and just practice, practice, practice. On the Blackboard site, I have some links on there. Under content, there's a folder that says nomenclature activities, which is all naming stuff. And there's a whole bunch of some little games you can do like naming different kinds of compounds. So there's little games on different compounds. It'll just quiz you over and over and over and over. So you can just really practice the heck out of it because it just needs to be just like you're speaking a foreign language. It just rolls off the tongue. Right? You can't sit there and think like, oh wait a minute, so something just needs to roll out the tongue. So practice makes perfect, right? So just like you're learning French or Spanish or anything, the more you do it, right, it becomes easier and easier and just second nature after a while. So same thing here. Okay, well, just a quick reminder, two kinds of bonds, ionic, covalent. We already know that. Ionic, you're transferring. Covalent, you are sharing electrons. Right, and ionic, we said, the metals are becoming the cations. They're losing the electrons. They're becoming positive. The nonmetals are becoming the anions. They're gaining the electrons. They're becoming negative. Right, we said that. So what happens? Well, they transfer as many as they need to until they get the noble gas configuration, right? Which is why the ones in group 2 are 2 plus, and why the nonmetals that are 3 away are 3 negative, right? So we already went over this. I'm just giving you a quick little review, right? But the goal is I want to get a noble gas configuration, all right? So we already saw this. Sodium has 1 valence electron, so it wants to lose it. Chlorine has 7, it needs 1 more. It wants to gain 1. So that's what happens. Sodium gives it to chlorine, and then they're happy. Sodium becomes 1 plus, chloride becomes 1 negative. Now they're happy, right? This is all kind of review here, so I'm going to fly through it. How about oxygen? We know, right? Oxygen is in group 2, not group 2, I'm sorry, not group 2, it's in group 6. It's 2 away. So it needs 2, right? It has 2 holes if you do the Lewis dot structure, all right? So it wants to become 2 negative. So it needs 2, so 1 sodium won't do it because 1 sodium only has 1 to give, so it needs 2 sodium, so Na2O, if you just did all that. Okay, I'm breezing through this. Okay. Now, how about molecular compounds? So molecular compounds, this is where they're sharing, right? So now they are not transferring. They're going to share the electrons. So one nonmetal offers an electron, the other nonmetal offers an electrons, and they just reach out and just hold hands, basically, and they're going to share the electrons. Versus, like I said, then in the last case, the metal has an electron and totally just gives it to the other one. So it's transferring. So we're going to share now on this point. So we're going to practice drawing actual structures for these molecular compounds. How do they actually share them? So I'll just give you a little example. Let's say we were going to combine hydrogens and oxygens and make a molecular compound. Because, again, they're both nonmetals, so it's going to be a molecular compound. So, hydrogen has 1 valence electron, right? It's in group 1. So if you drew it, you would draw H with a dot, right? Oxygen is in group 6, so it has 6 valence electrons. So you would draw 6 dots like that, right? Okay, so how many more electrons does hydrogen need in order to get a noble gas configuration? So how far away from the noble gases is hydrogen right now? 7 away? Find it on your periodic table. It's only 1 away. If it gets 1 more, it becomes just like helium. Remember? Helium's the so hydrogen only needs 1 more electron. Oxygen needs how many more, though, to get? Oxygen needs 2 more. Okay. So what they're going to do is they're going to share electrons and try to make some little combination where they could all work out. So you can imagine 1 hydrogen shares here, let's say. Well, so that helps out with 1 place, but oxygen still needs 1 more, right? So maybe you have another hydrogen come in there. Maybe something like this when you get done. So now when you're all done, everybody's happy. So when you're done here, oxygen has its noble gas configuration because it's got 2 around it. And oxygen has its noble gas configuration because it's got 8 around it. You see that? So at the end, they're all happy because hydrogen has 2 just like helium. Oxygen has 8 just like neon. So they wound up with noble gas configuration. But again, in this case, they're sharing them instead of transferring them. They're not getting this, they're just sharing them. Okay? Now the ones that are being shared, these ones, let me use a different color here. These ones that are being shared right here, see those? Those we call bonding pairs. So this is a bonding pair of electrons, a bonding pair. Okay, so is this one right here. Those are bonding pairs. But the ones up here that aren't being shared, see these up here and down here, the ones in yellow there I made? What do you think those are called? Pardon me? What'd you say? Non-bonding pairs. Man, you are smart. See, you already knew this. These are called non-bonding pairs. They are also called, anybody actually even hears more often, lone pairs. So the pairs that are being shared between the atoms are the bonding ones. Those are actually making these covalent bonds. The ones that are not being shared, they're called non-bonds, like I said, or lone pairs is the more common phrase. You probably can call it lone pairs a lot more. Okay, so you see how that happened, right? So this again is again, these are called covalent compounds sometimes because we have covalent bonds. So we're sharing these covalent ones here. Okay. So how about nitrogen, let's say, for example. So if you find nitrogen on your periodic table, how many valence electrons does nitrogen have? How many valence electrons? Not charged, it's not charged, we're molecular compounds. Nitrogen does not have 7 valence electrons. It has 5 valence electrons. In group 5, see that? It's in group 5. It has 5. It has maybe a total of them, but the valence ones, the ones in the outermost shell. Same as the group number. So it has 5, so it needs how many more to get an octet? It needs 3 more. So therefore we know that most of the time nitrogen likes to make 3 bonds. So in this case, if it's going with hydrogen, oh, well, it's going to need to partner up with 3 hydrogens. So can you see that? So 1, 2, and then 3. And then at the end, we're all happy because nitrogen has its 8. Every hydrogen has its 2 for its duet. Now you notice what we'll do is we will take these bonding pairs right here, and normally the way we'll write them instead is as a little line like this, or what's called a bond. So the bonding pairs are normally written as lines. So whenever you see a little bond like this, a line, that means there's 2 electrons being shared. So here I've got, oh, here's a bond. Oh, that's 2 electrons being shared. Maybe I'll write shared. Oh, here's 2 electrons being shared. Oh, here's 2 electrons being shared. So those are the bonding pairs. They're being shared now. Okay, so what is going to make a compound? Again, a molecular compound with carbon. How many bonds do you think carbon would want to form? So carbon has how many valence electrons? 4, so it needs how many more? 4, so it's probably going to make 4 bonds, right? Because it's going to try to share 4 different times to make, right? If it shares 4 times, it'll get 4 more, and it'll get its 8 it needs. You're exactly right. So carbon needs 4, so with hydrogen, it's going to make 4 bonds at the end, right? Okay, this is kind of a longer way of doing this, but I kind of want to show you that you kind of predict basically how many bonds an element's going to have in a molecular or a covalent compound. Again, this only works for the ones where we're sharing. Okay, the molecular is the covalents, not the ionics. You can't predict it with sodium or whatever. You can't do this kind of thing. Okay, well there is a nice little stepwise way of doing this. Remember these little things here. These little things here were called Lewis dot structures. Remember, so the whole thing together is also called Lewis structures. So now sometimes though, when you share, you may actually share more than 1 electron with the same atom. Maybe you share 2 electrons. So for example, hydrogen is just each hydrogen shares 1 electron. They're have a total of 2 share, that's 1 bond, or what's called a single bond. But let's say it was oxygen. Well, I told you oxygen is one of the 7 diatomics, right? Which means you never find it by itself. Well, now we can kind of see why you would never find oxygen by itself. Because oxygen has how many valence electrons? 6. So oxygen by itself is not happy, is it? Right? It's not happy. It needs, how many more valence electrons will it need? It needs 2. So what it can do is it could share like this with itself and make 1, and then it could share again with itself, like so. And then when you get done, you would have 2 shared pairs. So you might draw it like this. Now there's 2 pairs being shared, and then there's still those lone pairs out here that weren't touched, right? The lone pairs are still here.
Can you draw 2 lines?
So, yeah, so you draw like this. Now you draw, so now you draw, no, you're good. So now you draw 2 lines. So again, every line says there's 2 electrons being shared. So 2 lines tells me there's 2 times 2, 4 electrons being shared. Now, how about nitrogen? Okay, so again, nitrogen has how many valence electrons? 5. So it needs to share 3 more. So yeah, so again, okay, so for N2 for nitrogen then needs 3 bonds, and it can just actually make all 3 with itself. So one nitrogen gives up its 3 singles, the other one offers 3 singles, and they hold hands 3 times and make a triple bond. So again, 3 bonding pairs, or I could write this as 3 lines, means the same thing. So that's called a triple bond, because there's 3 bonding pairs now, 3 shared pairs of electrons. So again, every line is 2 shared electrons. So that's 2 electrons, that's 4 electrons, this means 6 electrons being shared. Got that? 2, 4, 6. But the end goal is still the same. They're trying to get that octet, right? So you see here for nitrogen, it's all happy because now it's got, did not mean to do that. This nitrogen has 8. This nitrogen has 8. So they both wind up with their octet. They're both happy in the end. Okay, well, let me show you a little stepwise way of doing this, doing these Lewis structures. I'll skip this for now. Okay, so write down these 5, 6 steps, whatever it is. Please write them down. I will go slow because we're going to use these steps over and over today, and we're going to practice it in lab. Whenever your lab is Wednesday, we're going to practice it, do this exact same thing. We're going to do this over and over in lab on Wednesday too. So, step 1, count the total number of valence electrons. The total number of valence electrons. We're going to count them all up. So I'll wait for you to write that down, and then we will do it. Determine the total number of valence electrons, or count them up. What do I say? Count the total number of valence electrons. Okay, so let's do that. So every nitrogen gives how many valence electrons? Everybody find nitrogen. How many does it give me?
5.
Everybody sure? Give me 5. Every fluorine gives me how many? 7. So, and I have how many fluorines? 3. So what's my total number of valence electrons? How many? It's not rocket science here. 26, yes. 5 plus 21. 26, right. So my total valence electrons would be 26. Okay, so that means that my structure, when I'm all done, it has to account for all 26 electrons, either bonding pairs or non-bonding pairs. When I add them all up, there ought to be 26. No more, no less. Okay, step 2. We're going to write the symbols of the atoms arranged in some kind of a way that's going to show how they're bonded to one another. So we're going to try to figure out, okay, so is the nitrogen bonded to a fluorine, bonded to a fluorine, bonded to a fluorine, or is it the fluorine bonded to a nitrogen to a fluorine, or what's the order? And there are some little rules here that will make this really easy to figure out. So the first rule says, typically, Whatever atom in your formula is in the center is the one that only appears one time in the formula. So in our case, there's one nitrogen and there's 3 fluorines. So the one that only appears one time is the nitrogen. So nitrogen probably goes in the center of the molecule, and everything else is around it. Okay, that's one possible rule. Another little possible rule is if you have a molecular compound and it's made up of hydrogens, oxygens, and something else, well, the something else goes in the center. So, for example, if it was HNO3, well, that's hydrogen, oxygen, and nitrogen. Oh, the nitrogen goes in the center. Or if it was H2SO4, oh, the S is the something else, and the sulfur goes in the center. Okay. So if it's hydrogen, oxygen, plus an element, that other element goes in the center. And the third little rule that'll help you out is if there's carbon in the compound, carbon's going to go in the center. Carbon loves to be in the center because it likes to have, we saw, 4 bonds. So it's really hard for carbon to do anything else other than make lots of bonds in the center. Okay, so again, back to NF3, our example here. Which element's going to go in the center of the molecule? Well, I said it's going to be N, right? Because there's one N and there's 3 F's. And rule 2A there says the one that only appears one time goes in the center. So I would put nitrogen in the center. Oh, I forgot to mention this. Well, last one. H and F are never in the center. Why? Because H and F can both only make one bond. Because they only need 1 valence electrons. So N would go in the center. And then I would just kind of spread the F's around it somehow. Just kind of put N in the center and put the other atoms all around it. So in this case, there's 3 F's, so I would just put 3 F's around it. Can you see that? Okay. So you got N in the center, and we got 3 F's. Okay, now we're going to actually go through and try to connect these. So we're going to connect them all with a single bond. So we're going to draw a line between each of these. 1, 2, 3. So I drew 3 lines. How many electrons are there in each bond? There's 2. So I'm going to subtract 2 electrons from my total for every bond that I drew. So I'm going to subtract how many electrons then? 6, right? So I had 26. Now I'm going to subtract 6. And I have 20 left. So you're always going to keep like a little running total going. So it was 26. Now it's 26 minus 6, 20. I'm going to keep on keeping running total until we get down to 0. Because our total is 20. We're going to keep on subtracting, using them up until we get to 0. When we get to 0, you know you're done. Okay, that's the first thing. So you drew a line between every one of these. Every bond is 2 electrons. I drew 3 bonds. That was 6 electrons. Okay, but these atoms still don't have their lovely noble gas configuration yet, right? So, how many more electrons does fluorine need before it's happy? So right now, fluorine has how many electrons? How many's it got right now? 2. How many more does it want? It wants to get up to 8, right? It wants 6, right? So the next step is we're going to start putting them on as the non-bonding pairs or the lone pairs. And we're always going to do the peripheral, the outside atoms first, and we'll do the center atom last. And then there's this little thing here that says start with the most electronegative element. You don't really know yet what that means, but we'll get to that shortly. So just make a note of it. But the big thing is do the outside ones first and do the center atom last. So that's 4A. Do the peripheral atoms first, give them all their lone pairs, give them a nice, happy, noble gas configuration. So you told me fluorine needed how many more? 6, which means how many lone pairs do I have to give it? 3, right? Each pair is 2, so I need to give it 6. So I need to give it 3 pairs. So I'm going to put 3 lone pairs around each of these fluorines, like that. Okay, we're getting closer. Now I've drawn 3 lone pairs, 3 lone pairs, 3 lone pairs. Everybody have this drawn? 3 lone pairs, 3 lone pairs, 3 lone pairs. Okay, so how many atoms, how many electrons did I use there when I did that? 6 and 6 and 6. I used 18. I still got 2 more that I got to account for somewhere, right? So first I used 6, now I use 18. I still have 2 left out of my grand total that I have to account for. Well, the next thing we're going to do, so remember, by the way, I mentioned this earlier, but yeah, but hydrogen obviously can only have 2 to be like helium, right? So yeah, so please with hydrogen, don't give it a lot of lone pairs. That doesn't make any sense. Okay, well, if there are still unused electrons, and there's still 2 left, well, we're going to give them to the center atom, because the nitrogen only has how many electrons right now around it? Right now it's got 2, 4, 6 around it, right? So it needs how many more? 2 more. Oh, look, there's 2 left. So I'll just put them, boop, right on the center atom. I'll put them right there. See those? Okay, we're almost done. One last step. Step 5 is the last one. Right, because I had 2 electrons here. I had 2 left, so they had to count for them. Okay, last step is, so if you're done writing, then we'll do a few of these for the next 15, 20 minutes. Okay, have that written down. Okay, the last step, step 5, says, oh, by the way, we're at 0 now, right? Because I just used 2 more. I used 2 more, so now we're at 0. So we got our goal. Okay, last step. Make sure the center atom has an octet. If it does not have an octet, begin turning non-bonding pairs or lone pairs into bonding pairs. I'll show you what that means in a second. But basically it says, if the center atom still doesn't have an octet and you've used up all of the electrons, then start taking those non-bonding pairs, those lone pairs, and start making them into bonding pairs. So just write it down, then I'll explain it. So you always check to make sure the center atom has 8 around it. If it only has 6 or 4, well, you're going to have to start doing some shuffling of electrons until it gets 8. Okay, so in our case, it did, right? In our case, the N had 8 electrons when you were all done. It had an octet, so it was happy, so there was no need to make anything other than just single bonds. Okay, let's look at a few examples here. So let me show you one here with SO2. Let's do SO2. SO2. So, let's just walk through the steps and then I'll explain this resonance structure thing. So, step 1, add up the total number of valence electrons. How many valence electrons do you get for sulfur? There's 1 sulfur, it gives you 6 electrons. That's 6 electrons. We have 2 oxygens. How many does every oxygen give you? 6. So that's 12. So what's my total number of valence electrons? 18. Are you with me? They're both in group 6. They both have 6. So I have to account for 18 valence electrons in my structure. Okay, which of those 2 atoms is going to go in the center, the sulfur or the oxygen? Why sulfur?
It's only one.
Because again, I said, right, rule 2a, the element that only appears 1 time in the formula goes in the center. So sulfur only appears 1 time. So I'm going to put sulfur right here in the center. Then I'll just spread the other oxygens just kind of out around it evenly. So I'll just put 1 on each side. It's probably the easiest thing to do. Okay, step 3 said, okay, begin to connect these by drawing a bond. Connect them like this. Every bond used how many electrons? 2, so I just used how many? 4. So I'm going to subtract 4 from my total, which leaves me 14. Right? Okay. Step 4 said, now take the remaining electrons and place them on there as lone pairs. But do the peripheral, the outside atoms first, and the center atom last. So how many more electrons does this oxygen need in order for it to be happy? It needs 6 more, right? It's got 2 right now, so I'll give it 6. 2, 4, 6. You with me? Okay, that used 6. How many does this oxygen atom on the right side need?
6.
Okay, so I'm going to give it 6. Okay, so I gave all the peripheral atoms nice, happy octets. All right? Try to make that a nice dot here, sorry. Okay, how many electrons did I just use?
12.
6 and 6 minus 12. I've got 2 left. Okay. Then it says on step 4, I think it's 4b, if you have any left, put them on the center atom as lone pairs. So I have how many left? 2. So I'm going to put on 1 lone pair like that. So then I subtract my last 2, and I have 0. Okay, yes?
Put one like on the top and then one on the bottom, I guess. Like this last pair.
Uh-huh.
Can you put one on the top and one on the bottom, or do you have to?
Well, I can only do one or the other because there's only 2 left, right? I only have 2 left.
Yeah.
So I can do it on top or bottom.
Or but can you do one on the top and one?
Like
on the
one.
bottom?
Oh, 1 electron, you mean?
Yeah.
Oh, no, you can't do that. No, you can't do that. That's what you're saying. No. Yeah, you can't do that. Yeah, they have to always be in a pair, either a non-bonding pair or a bonding pair. Okay, so here's where step 5 comes in. Step 5 says, double check to make sure your center atom has an octet. If not, then start doing some shuffling. So how many electrons are there on the center atom right now? It's only got 6, so it's short. It needs how many more? 2. Okay, well I can't just pull out 2 electrons out of my butt and just go, oh look, I'll just put 2 more there. Yeah, I can't just do that, right?
Would you have to make like double bond for one of the other electrons?
Right, so what I'm going to do, exactly right. So I'm going to take one of these non-bonding ones and move it over into a bonding pair. So your choice. I've got 6 different ones to pick from, right? See all these? I can pick from any of these. And I'm going to take one and I'm going to move it over and make it into another bond. So I'm going to make this bond, and then this one will go away. Whoops, I just erased way too much. Got to make it a little smaller. See what I did? So I took one of the non-bonding pairs and made it into a bonding pair. And then in the end, we're all still happy because Now sulfur has 8 around it, right? 2, 4, 6, 8. This oxygen still has 8, 2, 4, 6, 8. This oxygen still has 8, 2, 4, 6, 8. So same result, everybody got their octet. They did it with sharing electrons instead of having, like I said, to transfer, making positives and negatives. Okay, well the question is, as it says here, resonance structures. If you have 2 or more possible structures, because in this case, the pair that shared could have come from the left oxygen, or it could have come from the right oxygen, right? I could have done it, I could have made it single double, or I could have made it double single. I had 2 options there. Do you see that? So that's called resonance. So I could have done it either way. So when you have an option, we're going to draw them both and put a little arrow with a double-headed arrow between them, like this. I'm going to put a little arrow with 2 heads on it between them to show both. Because in reality, the molecule is actually doing both. It's a hybrid between single-double and double-single. So we're going to draw both possibilities and put a little arrow with 2 heads between it, which is called a resonance arrow. Everybody sees why there was 2 options, right? Okay, so that's called a resonance structure because it could be like this, it could be like this. In reality, instead of 1 and 2 and 2 and 1, it's about 1.5 each. It kind of spreads that 1 over both. We'll see, but you come back in 110 if you want. We will talk about that to your heart's content. So, okay, well let's try a bunch of these because we need some practice. So I'll just go through the first couple with you. Make magical sense of this. So, H2S. H2S. So get out your handout if you haven't already. I gave you lots of space in the handout to draw. Okay, step 1. Add up the valence electrons. So, I've got 2 hydrogens. I've got 1 sulfur. How many electrons do I get from the 2 hydrogens? Each hydrogen gives me how many valence electrons?
2.
Each one gives me 1. Yeah, right. Yeah, right. So, right, you're right. Like, everyone gives me 1, so I get a total of 2 electrons from the hydrogens. Right? Time out. Everybody sees that, right? Hydrogen's in group 1, so it has 1 valence electron to give, right? Okay. How about the 1 sulfur? How many does 1 sulfur contribute? Well, it's in group 6, so it's going to have 6 valence electrons. So I have a total of how many valence electrons to play with? 8. Awesome. Okay, which element goes in the center of the molecule? Why? Because it's by itself, and also H can never be in the center. You can never make more than 1 bond with an H. So I'll put an S there, and then we'll just kind of spread those H's around. So you can put 1 here, 1 here. Okay, what's the next step?
Combine them. Make bonds.
Yeah, bond them. So I'm going to make a bond here. I'm going to make a bond here. What does that do? What does every bond do? It means I used up 2 electrons. So how many did I use? Subtract 4 from my total. I have 4 left. What's the next step? Distribute them as lone pairs. So it says the first thing to do is make lone pairs on the outside ones. But in this case, hydrogen doesn't want any lone pairs, right? So please, for the love of the children, do not go, oh, hydrogen gets 6 more. No. All right, don't do that because hydrogen only needs 2 to be like helium, and it's already got 2. So where do they go then? Okay, so sulfur right now has how many? 2, 4, which means it needs 4, and there's 4 left. Perfect. So I'm going to put 1, 2, 3, 4. So now I subtract my last 4, and there's 0 left. Step 5 says check and make sure the center atom has an octet. If not, start making multiple bonds. Does the center atom have an octet? Yes. Boom, we're done. That's it. Yes? An octet means it has 8. 8 electrons. Does it have 8? It's got 2, 4, 6, 8. Yeah, it's got 8 electrons. Yep, that's the octet rule. Okay, let me try the next one with you. SiF4. So step one, add up all of the valence electrons. So I've got a silicon and I've got 4 fluorines. How many does each silicon contribute? 4. How many does each fluorine contribute? 7, so that's 28. So I have a total of, 32 valence electrons to account for. So when I'm all done, I got to have all 32 in there. I can't have more, I can't have less, else I've done something wrong. Okay, which element will I put in the center? Silicon, Si, because it's the one that's by itself. Yeah, so now I have 4 F's. Right, you're exactly right. You're exactly right. And you're right. And also said F can never be in the center. H and F can never be in the center. Okay, so I'm going to spread these F's around. So kind of like grades. I'm just going to spread F's around. Everybody gets an F. Everybody gets. No. So spread the F's around. Okay. So next step, do what? Bond them. I'm going to bond. So I made 4 bonds. So how many electrons did I just use?
16.
No, not yet. 4 bonds times 2. I used 8. So I have 24 left. Okay. Now I'm going to take those 24 and start putting them on as lone pairs. First I do the ones on the outside first. What's called the peripheral atoms first. So how many more electrons does each fluorine need? So right now this fluorine has 2, right? Every fluorine has 2 right now. See? 2. This one has 2. This one has 2. This one has, so each one needs 6. So I'm going to give every one of these 6. Okay, I gave them all 6. So now they each have what they want. They have 8. How many did I just use up? 6 times 4, I used 24. I've got 0 left. Amazing how that works out. And the last thing I do is I check to make sure silicon has an octet. If not, then I'm going to start moving some of these and make double bonds. Does silicon have an octet though? Yes, it's got 2, 4, 6, 8. So it's happy. I'm happy. You're happy. We're done. The universe continues rolling. Okay, your turn. Try CS2. Try CS2. How would you name CS2? I'm sorry, what? Okay. No, okay, you're right. Try C. PCl3. I'm sorry. How would you name PCl3? How would you name that? Not a trick question. Phosphorus trichloride. Right? Yeah, phosphorus trichloride. Yep. 2 nonmetals. Use the prefixes. Yeah, try phosphorus trichloride. Try it out. Talk it over when you get an answer. Help each other out. 20 minutes left. Okay, well, every atom, except for hydrogen, needs to have 8 total. So right now, because we need an octet column, then they have 8 that's the same as normal gases. So right now, this fluorine had 2 next to it. See that? So it needs how many more? 2, it needs 6 more to give it 8. So now it's got 2, 4, 6, 8. This fluorine only had 2, so it needs 6 more. Hydrogen, because hydrogen only needs 1, 2 to react with normal gases. Every other one, so fluorine needs 1 more. Not 1 more, but it needs 8. So every other element needs to be like neon, which is 8, or argon, which has 8. All of these are in group 8, so they have 8 valence electrons. So every other element, so sulfur, silicon, fluorine, whatever, phosphorus, 20, all has 8. help each other out. What do you guys get for PCl3?
Does it
Good.
CL since it's
Good. Talk it over.
It's only one more. Oh no, because it
No,
has
because this
two.
is only two, yeah.
Oh, wow, that's good. Okay, compare PCl3. Did you compare with somebody? Because I see different structures. Let me see what you got there. Yours is different from hers. Your shoes are different. Oh, you're not done yet? Okay.
No, I think so. Okay, so 1, 2, 3, 4, 5, 6, 7, 8,
Yeah.
18. Oh, there you go.
And this only has 2, 4, 6 right now, so it can't be done. There you go. Okay, so let me do PCl3 with you real quick. So 1 phosphorus, that has 5 electrons to contribute. 3 chlorines, those each have 7, so that's 21. We have a total of 26 electrons, right? So phosphorus is by itself, so it goes in the center, and then we'll just kind of spread these around evenly. Just kind of spread them around here, you know, a little triangle or something, whatever you want to do. Then I'm going to bond them. Bond, bond, bond. 3 bonds, that means I used 6 electrons. So I have 20 left. Okay? Now, first we're going to take these and give them as lone pairs to the outside atoms first. So every chlorine currently has 2, so every chlorine needs how many more? 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So that used 6, 6, 6. Antichrist. Oh. We got 2 left. 2 left. So where do they go? Well, phosphorus only has 2, 4, 6. It would love to get 2 more. And there's 2 left. So I put 2 there. And we use them all up. Last thing to always do, check and make sure that center atom has an octet. And it does. Phosphorus has 2, 4, 6, 8. So it's happy right now. Okay. Have you tried the next one yet? Okay. So let me do it with you because the next one's a little wacky. So we got 1 carbon. Every carbon gives 4. I've got 2 sulfurs. Every sulfur gives 6. So I have a total of 16 electrons. So I said, whenever you have a carbon-containing compound, carbon's going to go in the center all the time. So I'll put my sulfurs around here. I make a bond, make a bond. So that used up 4, so I got 12 left. Give the outside ones their octet. So this sulfur has 2, it needs 6 more. This sulfur has 2, it needs 6 more. Okay. Now I'm out of electrons. Now here's the number 1 mistake students do on this. They always just keep going like, oh, well, carbon must need 2 more. They just keep going like this and just pull them out of their butt. There aren't any more electrons left. I already used them all, right? So you got to stop when you're out of electrons. So next step says, okay, we're done. Make sure that center atom has an octet. It does not. Carbon right now only has 2, 4. I don't know what happened to that little line there. Give it that little line. Let's just have one there. So I got 2, 4. So what do I got to do? Well, I'm going to start shuffling those non-bonding pairs and make them into bonding pairs. So again, your choice. So maybe this one will move over here and become a double bond. So now it's got how many? Now it's got 6. Well, I need to do it again. So maybe I'll do it over here on this side now. Now it's got 8. So this one went bye-bye, and this one went bye-bye. So the question always comes, well, couldn't I just do it twice on one side? instead of one on each side. And yes, you could do it that way. Although generally though, the best way is to have symmetry. We'll see, to do like both equally rather than all on one side. Again, there's a whole way you can calculate this. The right way, it's called formal charges, but we'll save that for 110. But in general, the easy way to think of it is try to make it as even and balanced as you can. So rather than doing 1 and 3, do 2 and 2. Okay, I don't really have time to do the last one, but I just want to point out the first thing. This is nitrate. Notice it has a negative charge here. What does a negative charge mean on something? It means it has picked up an extra electron, right? So if I have one nitrogen, that means I've got 5 electrons, right? Then I've got 3 oxygens. That's 3 times 6, that's 18. And then that one negative means 1 more electron. So it's actually a total of 24 when you're doing this. So, again, I know you probably think, oh, it's negative, so you subtract an electron. But no, remember, negative means it actually gained an electron. So, if it was a positive number, let's say it was ammonium, NH4 plus. Oh, plus means it lost an electron. Then I would subtract 1 from the total. Or how about phosphate? PO4 3 negative? That means I would add 3 electrons onto the total. Whatever that charge is, okay? So you add 1 electron for every negative charge. You subtract 1 electron for every positive charge. You add 1 electron for every negative charge. You subtract 1 electron for every positive charge. Okay, so I'm going to do it super quick because I only got 10 minutes to do the rest of the chapter. So N goes in the center. I put 3 O's around it. Connect it first with 3 bonds. That used up 6, right? Leaves 18. So every oxygen has 2, so it needs 6 more. So give them 3 lone pairs. 3 lone pairs. So 6, 12, 18, right? So that used up all 18. So I'm out of electrons. But the center atom still does not have an octet. So I've got to take one of those lovely non-bondings and make a double bond. Where do I do it at?
Bottom. The middle one.
I mean, it's this oxygen, or this oxygen. It can be any of them, right? It could be this one, or it could be this one, or it could be this one.
Would it be better to do the bottom one since it's more symmetric? For example, like the 2 on the left and right hand side?
It's not really symmetric because it's like a triangle. It's not really like a... So it could be any 3. So I got to draw all 3. Because that is called resonance structures. So yes, it could be double bond here. And then singles everywhere else. This is really messy. I'm so sorry. Or double arrow. It could have been double bond on the top right one. And then single bonds everywhere else. Or, I guess I'll do it here. It could have been the bottom one, could have been double bond. And then single bonds everywhere else. Yes, normally I'd have written it out in a big line, but I ran out of room. Okay, the last thing though to do, it's a little different, is I have to show that charge. Because it is negative charge overall. So I'm going to put square brackets around the whole formula, maybe. And then put the charge up there. So I'm going to do that. Square brackets, negative. Square brackets, negative. So whenever you have a charge, put the formula in square brackets and put the charge up there on the top right. As a little.
If it was positive charge, what would you do?
I just put positive up there. Put positive or 2 plus or 3 negative, whatever it is. I put the charge, whatever it is up there. Okay, so we will do a bunch more of these in lab on Wednesday for practice, so do not fret. We will do more of these. Okay, well, okay. So what I've just shown you then is the way to figure out the way atoms in a molecule are actually going to be connected. Okay, so sulfur is connected onto an oxygen or whatever it is. But those little drawings though were all just flat two-dimensional representations, right? So it's just a flat piece of paper, right? So it's not actually showing you then the actual three-dimensional shape, which is really important, especially like in biology. The actual shape of the molecule, the way it's bent, has everything to do with all kinds of stuff you would never suspect. Like it has to do with the reactivity, with the phase, if it's a solid or liquid, based on the shape. Its color, is it magnetic or not? How does it taste? Is all about the shape. How does it smell? All about the shape. Is it toxic or not toxic? All of these things are all based on the shape of the molecule. Yeah. So you probably know, for example, here, enzymes, right? So in enzymes, you might know from biology class, they have a lock and key mechanism. So the shape of the enzyme will fit perfectly then into the molecule that it's trying to break down. Or for neuroreceptors, the shape of the neurotransmitter will fit perfectly then into the neuroreceptor part. So it's all about the shape. So it's crazy. You can have the exact same molecule, so that's a molecule. That same formula for a molecule, and let's say it's linear and it smells like, cranberries, and then you bend it and now it smells like farts. Or it's straight and it's totally healthy, you bend it, now it's toxic. Or it's, crazy. All it is the shape. I said literally the shape is bending it, changing it, will totally change it to make it magnetic or not magnetic, or toxic or not toxic, or smells different, tastes different, whatever. So it's really important then that we know. So the way that we do this, figure out what is the three-dimensional shape, is this big, long, scary term, but it's pretty easy, really. VSEPR. VSEPR, which is an acronym for valence shell, VS, electron pair, EP, repulsion, R, theory. So VSEPR theory. VSEPR theory. So we were just drawing these structures, and we were taking, basically, in those structures, all of the valence shell electron pairs, and we were placing them around the atoms. So this theory basically says, okay, so now you have all of these valence shell electron pairs, and these electrons are all negative. And when you try to get a bunch of negatives near each other, what happens? They're going to repel each other. So this theory basically says all of these pairs of electrons that you placed, they are going to try to repel each other and try to get as far away as possible. So they want to minimize the amount of repulsion. They want to get as far away as they possibly can. That's all that says is, okay? So all these valence shell electron pairs you've created, they're going to try to get as far away as they can in order to minimize the repulsion. Okay, so let me show you some examples, and then you'd be like, oh, okay, I see what you're talking about. So first off, the electron groups, so make a little note, they can be a lone pair is a group of electrons, but any kind of bond is a group, whether it's single, double, or triple. Okay, if it's 2, 4, or 6, they're all still in that same bond. They're still in that same group. So let's say, for example, you have an atom with a molecule then with a double bond. Even though it's 2 pairs, it's still, they're grouped together as 4 electrons in that double bond. So it's not like that's 2 groups. Okay, so I'll show you real quick. So let's say you have 2 things in your hand and they're both negative. Okay, they're both negative. Well, the best way then to minimize repulsion and to get them as far apart as possible is to put them both on opposite sides of you, right? So if you have 2 electron groups, you're going to have a linear geometry. So 2 electron groups will make a linear geometry. What if you have 3 different groups of negative charges and you want to spread those out as far as possible? Well, for 2 things, as far as possible is 180 degrees from each other. For 3 things, we're going to make them 120 degrees from each other, which is what we call trigonal planar. Trigonal planar. So 3 electron groups will form a trigonal planar electron geometry. And the last one, if you have 4 things, now you might think at first, oh, well, 4 things must be 90 degrees. And that would be true if molecules then were all 2-dimensional, but they're not 2-dimensional. Remember, they are 3-dimensional creations here. So actually, then in 3 dimensions, the maximum angle between 4 things is actually 109.5. You make this little thing like this. It's called a tetrahedral. And it basically then it kind of looks then like a little pyramid, basically, where you have 1 electron group on each corner of the pyramid. So that's called a tetrahedral. What's tetra mean again?
4.
4. What does hedron or hedral mean? You know? You know, like your geometry class. You know, polyhedrons.
Sided.
Yes, sides. So a tetrahedral has 4 sides. You can see, yeah, it's got like 4 faces here, then, if you will, on your pyramid. It's got 4 sides. It's called a tetrahedron. Trigonal planar is called trigonal because it's like a triangle, trigonal triangle, and it's planar. It's a flat triangle, so it's called trigonal planar. Okay, I've got 60 seconds. I don't think I can really do much with 60 seconds, so I think we'll wrap it up there. So Wednesday in lab, we are going to finish this chapter. So first. So bring your lecture stuff, bring your lecture notebook. We will definitely finish this chapter up, and then we're going to practice it, like I said, and do Lewis structures, build some molecules in, build some molecules out then in the lab then as well then. Now then as well then, some ball and stick models are covered when you actually, build them out, and we'll see these 3-dimensional structures. So, okay, I had a few people's things to pass back. Maybe they weren't in labs, so I don't know if they've been here today. Naya's not here. Mariella, that's me for you. Daniel. Sasha. Lauren. Aaron.
I know, but I know people to, yeah, I know what you mean. But it's like, this is good even thinking about taking summer classes.
That's it.
now.
Okay, we'll see you Wednesday. Bring your lecture stuff and your lab, your pre-lab, all that stuff, like always. So, we'll see you guys Wednesday.
I'll see you next class. Bye. Bye. You're gonna